First of all, I would like to acknowledge the traditional owners of Australian lands and pay my respect to the elders past and present, admonish the Burungon people. Today, I'm happy to present Andrey Chubukov, who is a William and Bianca Fine Chair in the theoretical physics in the University of Minnesota. He is one of the leaders in the strongly correlated physics, and especially in unconventional superconductivity in numerous platforms, unconventional magnetism, and strange metals. Andrey has made his PhD in 1985 in Moscow State University. In the beginning of 90s, he moved to the beginning of 90s after being a research scientist in Kapitz Institute for Physical Problems. He has moved to United States. In 1993, he has become a professor at the University of Wisconsin Madison. And in 2014, he moved to the University of Minnesota. Andrey has got several prestigious fellowships and awards, including John Bardeen Prize and the fellowships from the American Physical Society and Alfred Sloan Foundations, just to name a few. Okay, Andrey, the stage is yours.
Wonderful, thanks very much. Yeah, just to be sure, you guys can hear me, right?
Yeah, perfect.
Yeah, okay, wonderful. And so then request on my side to interrupt whenever you have questions. Don't let me go unanswered. And there are a couple of parts of the talk, so if I don't talk in length about the last part, it's fine. It's better if you will interrupt me and basically keep me honest during the talk. So I titled this as Twists and Turns of Superconductivity from Repulsive Interaction, but you will see where I'm heading. So as a colloquium, so let me start with something mostly, the first part will be for people who are not that familiar with superconductivity. So if you feel that I'm too slow, just let me know and I will rush a little bit. So first of all, superconductivity, zero resistance states of interacting electrons. If you take a non-superconductive metal, it's supposed to exist, then you get resistance that remains finite at zero temperature. If you take a superconductor at some point, which is called TC, resistance will jump to zero. And it's a long story. It started long ago with a nice story that is for after dinner talk rather than colloquium about how it actually started in 1911 and the importance of oversleeping, etc., etc. Nevertheless, Nobel Prize was given very quickly in 2 years for the discovery of this jump of resistance in mercury. And starting with this, let me ask a rhetoric question. What we need for superconductivity? And in a very simple and a little bit oversimplified language, I'll put it this way, that if we consider Drude theory of metals, something that you can easily find in textbooks, Drude theory of metals tells you that if you consider Ohm's law, it's based on Ohm's law, and there is a finite lifetime of fermion before collisions, so there are collisions between electrons, then current is proportional to electric field, proportionality coefficient is called conductance, and the inverse of conductance is conductivity. Inverse of conductivity is resistivity, and you see that rho is finite when even when temperature is equal to zero. There's no temperature here, except for the knowledge that lifetime of fermion in a given quantum mechanical state is finite tau. And it's a dissipative current. I mean that in order to sustain current, you need to constantly borrow energy from the source of electric field. So without borrowing energy, the current will just die off. At the same time, well before actual theory of superconductivity was developed, it was known on general principles that if somehow you have a ground state with macroscopic number of particles in the same quantum mechanical state, that's what we normally call macroscopic condensate. This macroscopic condensate has a wave function. Wave function has amplitude and the phase, and simple quantum mechanical consideration shows that yes, there should be a current related to gradient of this phase, and this current is by no means associated with or accompanied with energy dissipation, and it would exist even if electric field is equal to zero by itself. And of course, the fact that there is a current when electric field equal to 0 means that conductivity is infinite and resistivity is 0. It says resistance is 0. And so in this respect, the answer is very simple. If we have somehow macroscopic condensate, so mean macroscopic number of particles in the same quantum mechanical state, then we have a phase of this order parameter of the condensate wave function, and it produces U current in the absence of electric field. Great. Then for bosons, the appearance of such condensate is completely natural. We all know that these bosons tend to cluster at 0 momentum below particle temperature, and at 0 temperature, macroscopic fraction of bosons are clustering at 0 momentum, and this is called Bose-Einstein condensation. Fermions are fermions, and electrons are fermions, and Pauli principle tells us that two fermions simply cannot exist in the same quantum mechanical state, which means that they cannot condense. But next point is the logic is very simple. If somehow two fermions form bound state of two objects with spin 1/2 necessarily has spin equal to 0 or 1, it's a boson. Bosons do condense. So then what we need to condensation and for superconductivity at the end of the day is to pair fermions into bound state. And according to this logic, this is all we need. And of course, in order to pair fermions into bound state, we need attraction between fermions. So question obviously is where attraction comes from. But before I say where attraction comes from, there is a question how strong attraction must be. And here's the name of Leon Cooper comes in. In fact, it was done before Bardeen-Cooper-Schiffer theory of superconductivity. He realized that arbitrary small attraction between fermions is capable to produce bound state in any dimension because of something that distinguishes condensed matter and high energy theory. In condensed matter, the set of points with 0 energy is not with 0 momentum, but rather as finite momentum called Kf. It means that fermions occupy Fermi surface states inside the Fermi surface. And as a result of the fact that 0 energy state are at finite momentum rather than at 0, every time when you do integration over momentum in calculating any form of bound state, then essentially it doesn't matter 3 dimensions or 2 dimensions, you effectively reduces this to one-dimensional integration of k minus k. And one-dimensional integration in momentum, one-dimensional integration in frequency give you 2 dimensions, and in 1 plus 1 dimension or 2 dimensions, any arbitrary weak attraction will produce bound state. So this is called Cooper phenomena, and associated with this there are Cooper logarithms because of this 2-dimensional integrals that produce logarithmical singularities. And I will come to this logarithmical singularity later in the talk when I'll try to argue that in what I'm doing, situation is totally different.
Andrey, I think we have the first question. Alex, just please go ahead.
So, sorry, Andrey, I just got a bit lost in your explanation of the reason for the Cooper logarithm. So is it that the particles are at 0 energy, or that a pair of particles have 0 net momentum? You're taking them from opposite sides of the Fermi surface.
Pair of particles has 0 net momentum. You take them from the opposite side of the Fermi surface. Both fermions then will be simultaneously near the Fermi surface. And the point I was trying to make here is very simple, that if somehow the states with 0 energy would be at 0 momentum, then the result, whether bound state exists or not, would very much depend on dimension. If 0 energy state are at Kf rather than at k equal to 0, that any integration over momentum reduces to one-dimensional integration. So the problem reduces to one-dimensional in momentum space and one-dimensional in frequency space. And this problem, this is where logarithms appear, and this is where arbitrary weak interaction, attractive interaction, produce your bound state. That's all I try to say.
And so why is this different than high energy physics? Is it? Excuse my
ignorance. Suppose that energy is, that chemical potential is 0. Suppose that energy is just k squared.
Yeah.
All I'm trying, this is what I'm trying to say. Suppose you have just 2 particles in a vacuum, and you want to see whether 2 particles in a vacuum produce a bound state. Energy of each particle is k squared. Very good. But then suppose that you're in 3-dimension. You have k squared dk in numerator because of because of phase space. And you don't get any singularity of integrating out of two fermions with k and minus k near the Fermi surface. Then you need a threshold to produce a bound state. This is the difference, I guess.
Okay. Thank you.
Yeah. Okay, let's move on. So this is important point, that we don't need to worry about strength of attraction. All we need is an attraction. We don't need to overcome any threshold. So the next point is obvious: where attraction comes from. And here is the theory, which in my opinion, one of the, if not the best, most elegant theories of the 20th century, for which Nobel Prize was given, not next year, but several years after. And this theory basically said, look, we need foreign body to create attraction between fermions. And this foreign body is quantum lattice vibrations. So the story can be told in various ways, but basically what happens is that one electron comes in, creates lattice vibration, another electron comes into the same range of material and feels lattice vibration, and through lattice vibration, it feels other electrons. And through this extra body, which are lattice vibrations, two electrons effectively attract each other. And this was considered the dominant pairing mechanism for years. And for what is called conventional superconductors, no doubt that this is the correct mechanism. And this mechanism has been confirmed experimentally in many materials. Macmillan and Rowell did wonderful story about tunneling, interpretation of tunneling experiments. I want just to mention that even with this mechanism, there are still out questions that was somehow put under the rug in when this was discovered and this first discussed. For example, what is the role of Coulomb repulsion and how strong Coulomb repulsion should not be in order to not destroy this wonderful mechanism of superconductivity. There are people working on this subject right now, and with the advent of numerical studies, there are new results coming in. So I just want to say that this is not by any means problems to which a big dot is put and everything is in textbooks. So we don't need to worry about any new stuff here. There is new stuff coming up. But on general in terms of general wording, it's really like this. There is a mechanism for two electrons to attract each other by introducing something else, vibrations, quantum lattice vibrations, phonons. And then development was pretty steady, starting from 1911. And suddenly, critical temperature where the system becomes superconducting went up almost vertically in 1986. This is where the new era began. It's started with cuprates, and the new era has a name, high temperature superconductivity, although not all the materials studied in this era are actually high temperature superconductors in the normal sense of the word. And this was probably record Nobel Prize given next year after the discovery. And then, of course, new breakdown was in 2006 or 2008, depending who more carefully looked at the first paper. And this is superconductivity in iron-based systems, which record temperature here is in two-dimensional systems really is slightly below 100 Kelvin. But it's definitely a record in terms of Nature and Science publications, absolutely. Pretty interesting systems, and we'll discuss it a little bit later. So, and then the latest breakthrough is, of course, superconductivity in twisted bilayer graphene, and then some related systems like Bernard bilayer graphene, rhombohedral three-layer graphene, etc. These are the systems in which Valley index starts playing as important role as spin index. But nevertheless, this is a story about superconductivity under doping of system away from charge neutrality, very much like it happens in cuprates, very much like it happens in iron-based materials. I'm not saying physics is the same. I'm just saying that this is another example of superconductivity, which people actively study and actually asking the question, where does the attraction come from? And of course, there is a number of other materials. For years, superconductivity in heavy fermion materials attracted a lot of attention. Rutenate, titanates, nickelates, now Kagome materials. There is a hope for superconductivity in Kitaev materials. And this is all keeping the interest to superconductivity afloat, particularly as in many cases, we still don't quite understand what the mechanism of superconductivity is. And this includes twisted bilayer graphene. So first question is, I said at one point that it's a new era of high TC, whether only TC is relevant, whether the fact that TC in 1986 went up almost vertically is the crucial thing. And the answer is no. First of all, because some of the materials which I already named has TC of not that high. In twisted bilayer graphene, TC is few Kelvin. In pnictides, it's most of pnictides has TC in around between 20 and 40 Kelvin. And at the same time, this wonderful material, MgB2, which is for sure phonon superconductor, has TC of 40 Kelvin. This material has interesting history because it was available by mail for 40 years and nobody bothered to measure it, except for one group who measured it long time ago, up to temperatures around 55 Kelvin. They were very close to superconductivity, but they didn't reach it. And so they measured conventional resistivity that goes smoothly. If they would cool down a little bit, they would see that resistivity drops down vertically. And of course, not to let me mention that superconductors with highest TC are actually electron phonon superconductors. There is a wonderful studies under pressure for people who do actual studies, not who play the game with politics. And they found that, yes, already established that in hydrogen sulfide, there is a temperature, critical temperature about 200 Kelvin. In lanthanum and yttrium hydrides, TC can be as high as 250 Kelvin. So there is no such thing as there is no room temperature superconductivity. It exists, but pressure is high. And these are experiments that nobody doubts about. Okay, so with this, the question is what is relevant? And I'm coming to the end of my long introduction by saying that majority of people believe, not everyone, but majority, that if you take cuprates, iron-based superconductors, rutenates, heavy fermion materials, also organic superconductors, and try to see what TC you get if you consider electron-electron interaction. Then two things happen. First of all, some of these materials, as we discussed a few minutes later, are unconventional in terms of their pairing symmetry. And it's not that easy, it's possible, but not that easy to reproduce unconventional pairing symmetry with electron phonon interaction. That's number one. Number two, at least in some cases, the first principle calculations showed TC much smaller than experiment. For example, in the early days of iron-based superconductors, something around 2008, 2009, people did first principle calculations for electron phonon interaction, even neglecting Coulomb interaction, and found that TC would be 1 Kelvin, 60 times smaller than in the experiments. You can improve this number by doing here and there, a little bit here and there, but you cannot get 60 times larger temperature. And this brings me to the subject of today's talk, that if somehow for one reason or another, electron phonon interaction is not a player, say different pairing symmetry, TC obtained for electron phonon case is too low, then there are not too many choices in the world. And so pairing must somehow come from electron-electron interaction, because what else exists? Electrons interact with each other either with vibration of the lattice or between themselves. Between themselves, they interact with Coulomb interaction, and this interaction is repulsive. And so here is the subject of my talk: superconductivity from repulsive interaction, or how to convert water into wine, how one can possibly get a balanced pair of fermions out of repulsive interaction. And anticipating what I will say later, the very question, superconductivity out of repulsive interaction, I put it with exclamation sign but you will see that the question a little bit depends on how, from what angle you want to look at the problem. So let's do it. As I mentioned a few minutes before the talk, that some story began when I was just born, or even before. It was early 60s. And then two groups working totally independent from each other, as far as I understand. Landau together with Pitayevsky, and then Phil Anderson together with Morel, found pretty much the same answer. That if you consider what happens if you pair by generic repulsive fermion-fermion interaction. Although they didn't use the word repulsive, but let's assume that it's electron-electron interaction. Then first question is what you need out of this interaction. And they argued, and argued mathematically rigorously, that fermions can form bound state, not with angular momentum 0, which I discussed before. This is what comes from electron-phonon interaction, and it's what is called S-wave superconductivity. But they can form bound state with any arbitrary angular momentum. And what's more important is that if you solve for the pairing explicitly, you find that the pairing problem decouples between different angular momentum. What it means? It means that interaction can be very much repulsive. If you plot it, you find that interaction is pretty much at L distances repulsive. But if this interaction has at least one, or it's enough, one attractive component as a function of angular momentum, you expand interaction for rotational invariant systems. And this was all done for rotational invariant systems. So you expand it in angular momentum and find partial components of the interaction. And the message here is that if just one component is attractive, then it's sufficient because others will not interfere. Pairing problem decouples between different angular momentum. And then the next argument, which was not in their papers, but just was in the air, is that if you consider large angular momentum and ask from where this partial component come from, the larger is m, the larger are distances between two fermions from which this partial component comes from. And this brings me to something that I guess most of you know, that if you consider screen Coulomb interaction, the standard story is you replace 1 over r Coulomb interaction into Yukawa potential E2 minus r over xi. But almost equally well-known story is that this is not the full. And if you go to large distances, then because of robustness of the Fermi surface, your effective screen Coulomb potential start oscillating. And this normally associated with the name of Friedel as Friedel oscillations. In 3 dimensions, oscillation is cosine to KFR over r cubed. And the fact that KF is here means that this is really property of the sharp Fermi surface with radius KF. And because of oscillations, you occasionally, at some distances, has a situation when you have overscreening. Overscreening means that interaction changes sign and becomes negative, means for us attractive. It doesn't happen all the time. No, there are some regions where this happens. And of course, regions where interaction is positive is much wider than the regions where interaction is negative, except that if you go to very, very large distance. But the question is, if you want to consider partial component of the pairing interaction, is it enough that at some distances, interaction gets overscreened? And this brings me to the wonderful story by Walter Kohn and Kohn and Luttinger, who unfortunately died before winning probably 2 or 3 Nobel Prizes. Kohn-Luttinger's story, that the story of 1965, is that they took this seriously and they rigorously, mathematically rigorously, considered effect of Friedel oscillations on the pairing interaction. I put it diagrammatically as look as they considered second order diagrams, which is not what they actually did. They rigorously included singular contribution from the Fermi surface on top of arbitrary, regularly screened interaction, which is repulsive. So the story about Friedel oscillation is here in these diagrams. And what they found is that if you go to large angular momentum, then no matter what regular screening of interaction is, you always get attraction, at least for odd component of momentum, which means over-screening wins. Definitely, the word definitely means that the result that you get is minus full square. So you get a partial component of interaction with large odd M, which is negative full square. What is under the square doesn't matter. If it's negative full square, it's attractive.
Andrey, could I interrupt you?
Sure, go ahead, please.
As, you have mentioned that it becomes attractive at large R, at large scales. What gives the scale? Inverse Fermi momentum or something?
No, M, angular momentum.
I mean,
You take
for the previous slide, when you have sketched the Friedel oscillations, that
you go to large R. At large R, of course, you get cosine 2kfr over R cubed. If you are not at very large R, of course, your cover term is also there. Now, you're asking what's the scale of oscillations, if this was the question, sorry. The scale of oscillations, of course, set by Kf, by inverse Kf. That's why 2kfr is here.
How large is supposed to be R?
Oh, then another question is how R is related to M.
Okay.
And the answer is that the larger is M, the larger is R. I don't remember exact relation, but I think it's inverse linear.
Mm-hmm.
So R scales as 1 over M because it's basically 1 over M. I think it's 1 over M to 4th instead of 1 over R cubed. So basically it's almost, I think it's inverse linear. So means that larger M, for larger M, you need larger R.
Okay.
And this is pure quantum mechanics. You just take, you know, what you take. You take interaction, you expand in 3 dimensions in Legendre polynomials, which are eigenfunctions of momentum, and you find partial components. That's all you do.
Okay. Thank you.
Okay, very good. Yeah, let's move on. Very good. Interrupt me with questions. Yeah. So, but then message from them is very straightforward. Is that definitely you take nominally complete repulsive electron-electron interaction, and you find out that over-screening wins at large angular momentum. What is the minimum momentum with over-screening wins? They didn't answer, in fact, although they could. And it's a separate non-physics, but more social story, why they didn't answer this question. They were too honest, really, to look into something that was not that rigorous compared to completely rigorous stuff that they did. So anyway, their statement is that as a matter of principle, system in rotationally invariant system is always unstable towards superconductivity because Friedel oscillation at large distances produce the attraction with a state with large angular momentum. That's what they say. And this was first example of how to get superconductivity out of repulsion.
Andrey, could I interrupt you again?
Absolutely, go ahead.
Yeah. So based on these diagrams, it is beyond RPA screening. Am I correct?
Yes. Oh yes. All RPA screening is this wave, this dashed line which I put here.
Mm-hmm.
Any regular screening is here. Although one has to be careful, it's not RPA, but what you get is this diagram, the last one, right?
Mm-hmm.
Can be considered as part of RPA. It's a bubble.
Yeah.
But what you do is this: inside the bubble, there is a singularity at 2kf. And this singularity at 2kf is exactly what gives you Friedel oscillations. So what they did is this: they said, let's assume that we incorporate all regular RPA-like screening, and aside of RPA, anything regular. What it means regular? Means that any, if you take any analytic function and expand it in Legendre polynomial, partial component scale as e to minus m. They're exponentially small in m. On top of that, they said, look, all these graphs that I showed here contains polarization, particle-hole polarization. And at 2kf, this particle-hole polarization is singular. There is a singularity in the derivative. And you ask, what the singularity of derivative means for partial component with large M. And answer is because of singularity, because of this non-analyticity, partial component goes 1 over m to 4th power. Power law except compared to exponent. Then they said, take this dashed line as arbitrary function of momentum. We don't know what it is. It's some function, some repulsive, some regular interaction. Bare term will be not interesting because it gives partial component e2 minus m. In all these graphs, you basically calculate the leading effect of non-analyticity. And you find that it's 1 over m to 4th times some combination, in fact, of u of 2kf and u of 0, because in order to get polarization bubble with 2kf, you will find that some interaction need momentum transfer 0, some need momentum transfer 2kf. And then you find out, first of all, you need to do it only 2nd order, because if you include one more singularity, you get 1 over m to 8th power. So if you want leading 1 over m term, you do it once. And then you calculate explicitly what is the coefficient in front of 1 over m to 4th power. And as I said, for odd m, they claim that it's negative full square. Under full square, there's some combination of u of 0, u of 2kf, but we don't care about what is inside the full square. Did I answer? Can I move on?
Okay, thank you.
Yeah. Okay, let's move on. More simple version of what I just said. Let's assume that we have a simple Hubbard interaction, which means that it should be delta function. It's just different font. U delta function of R, which means that regular screening is so strong that Coulomb repulsion only holds when two fermions are at the same lattice side, obviously with opposite speeds. More simple calculations. Now it's really 2nd order. This is not that rigorous as Kohn-Luttinger, but nevertheless, 2nd order calculation. And then there is one simplification of the story that will be with us for the next 20-something minutes. If it's Hubbard interaction on a bare level, you don't get anything in channels except for m equal to 1. It's constant interaction. So it only has m equal to 1 S wave component. It doesn't have any other component, simply because constant. If you integrate with Legendre polynomials, of course, it will give you 0. So you start with 0 in all our channels besides S wave. In S wave, you have repulsion. You do calculation to 2nd order in U, and you find out that all channels starting from P wave from m equal to 1 becomes attractive. And this was done a few years later by Fein-Lauser. And the outcome of this work is that for Hubbard interaction, you get simple result. If it's attractive, you get S wave. If it's repulsive, you get P wave. And interestingly enough, this result holds in both 3 dimensions and 2 dimensions, although in 2 dimensions, calculations are much more involved than in 3 dimensions. Great. That was history. Rotational invariant system, because at that time, the idea was to understand pairing in helium-3. But what about real lattice systems? This
Andrey,
is what I want.
Just before we come to reality, can I just ask another question?
Go ahead, please.
On previous slide. So my understanding of the interaction is it's due to the Friedel oscillation. But if you have point Coulomb interaction, there's no Friedel. Is there still a Friedel oscillation on this Hubbard model?
But when you start renormalizing it, you start getting interactions that will be function of R.
So the 2nd order U brings in an
at 2nd order, you get interaction which will start oscillating. Yes.
Okay. All right. Thank you.
That's exactly what it was done. You start with U's and you dress U. You get effective U as a function of R, and then read off what is the partial component of that interaction. The trick here is that in original Kohn-Luttinger, you have to argue that your regular interaction was there, and it was formally larger by magnitude than any screen, any part that Kohn and Luttinger included. The game was this exponent e2 minus m versus 1 over m to 4th. Here, the game is much more simple. It says that you just have nothing to order of U in channels except for S wave. And S wave will remain repulsive no matter what. And then what you get in order U square is the full result. There is nothing to compare with. There is no other part. So this was where the game was here. It's call it in any way, but this is what was done.
Thank you.
Okay, real systems, real life. Let's see. First statement is negative. We don't expand in angular harmonics because in any lattice system, of course, there is only finite number of irreducible representations, which basically means that if you keep expanding in angular harmonics, they are no longer orthogonal except for few. As a result, there is no factorization besides, again, few harmonics, and there is no exact proof that any system might become superconductor at low T. Statement is that in a lattice system, you may have normal state down to 0 temperature. The system doesn't have to become superconductor. And in fact, now we have at least one example where interaction is strongly renormalized but remains repulsive. However, for many systems that I mentioned before, it turns out, and I will try to argue this, that Kohn-Luttinger type reasoning, not reasoning itself, not reasoning per se, but Kohn-Luttinger reasoning in spirit, gives good understanding of superconductivity from repulsion. And with this phrase, I just meant one simple thing. Don't take bare interaction between fermions. Include screening. See what you get when you consider screen interaction, or mathematically we call it fully irreducible interaction in a particle-particle channel, which means interactions that includes all renormalization from orthogonal particle Hall channel. And then see what you get. That's what I basically just said. I'll give you a few examples, and I will try to run this part rather quickly because I look at how much time I left, and I want to tell you something more novel, etc. But nevertheless, because of connection to the next part, I will start with pnictides, although historically everyone would start with cuprates. Pnictides are, for those who didn't work on them closely, these are materials, which are many of them. They can be electron doped, they can be hole doped, there is also isovalent doping, but general story is like this. Without anything, the material is magnetic. It displays what's called stripe magnetism. You dope either by hole or by electrons or by isovalent doping, and the system becomes a superconductor. And there is also nematic phase that attracted a lot of attention, but let's focus today on superconductivity. If you look at fermiology of the system, first, when I looked at this, I said, I don't want to work with this system because it's a zoo of states, many 5D orbitals, and really zoo of electronic states if you look at the whole scale of energies from -2 electron volt to 2 electron volt. But if you zoom into very low energy states near the Fermi surface, situation becomes a little bit more clear. There are several pockets, meaning states for small Fermi surfaces, and some of them what is called hole pockets when dispersion goes down, means that occupied states are below, are at here, if I can use laser pointer. It's actually at negative energies. And there are electron-like Fermi surfaces when dispersion is normal and occupied states are basically at near the bottom. Here, for hole pocket states near the top are unoccupied. And the hole pockets and electron pockets are separated in space. Then zoo of the story is that depending on materials, there are 2 or 3 near circular hole pockets around gamma point 0, 0, and there are 2 elliptical electron pockets around pi pi. So it's really pretty much zoo. But if you allow me for a second to go into pedestrian level and just say I want to simplify the problem as much as possible, then I would say that from general perspective, I need to play the game with the presence of Fermi surfaces, one near gamma point 0, 0, and one near corner of the brilliant zone, which is this particular case at pi pi. The fact that I showed you 4 Fermi surfaces means nothing because it's just equivalent points in the brilliance zone. And I will not at this point even play the game with that one is hole, one is electron. What I want to do is to do something in spirit of Kohn-Luttinger. Namely, given that there are two types of Fermi surfaces, or just two of them, I will just play a really simple game. I introduce two repulsive interactions. One repulsive interaction will be inside each pocket. I call it G1, and you will see notations through the remaining time of my talk. And I'll, for simplicity, use the same G1 for within hole pocket, the same within electron pocket. This is a repulsive interaction between fermions within a pocket. And I introduce another interaction, also repulsive, when I take two fermions from one pocket and translate into two fermions with the other pocket. This interaction is allowed because total momentum transfer is 2 pi, which is the same as reciprocal lattice vector. These are two interactions, both are repulsive. And first, without any renormalization, I just want to say what I know about superconductivity in this system. I introduce two order parameters, gap or order, superconducting order on hole pocket, superconducting order on electron pocket. I need to solve 2 by 2 problem. This is really kindergarten problem. And when I solve it, I found, as usual, for 2 by 2 problems, there are two eigenfunctions. And notations here is such that in order to get attraction means that eigenfunction is negative. So this is all what happens. I'm trying to understand what the sign of the effective interaction is so far without introducing any screening. And the answer is very simple. There are two of them. One is definitely repulsive. Sum of the two repulsive interactions, lambda A is definitely positive. And lambda B, well, it depends who is larger. Interaction within pocket or between pockets. Remember, we need negative lambda for superconductivity. And at this stage, let me go back to what Fein-Lauser did and say, okay, let's just for sake of the argument, consider that we again consider on-site repulsion U. Then remember, in momentum space, this interaction is constant. So G1 and G2 are exactly the same. And then to first order in U, I have one of these two, lambda A is definitely positive, but lambda B is 0. And consider lambda A and lambda B as some simple versions of what previously I called different angular momentum. And we'll see this. Again, this lattice system, I cannot expand an angular momentum, but I can have two different combinations of the couplings. And on top of this, let me do what I did a few slides before, screening. I want now to screen these two interactions, G1 and G2. They are originally the same, and this is why I don't know what I get, attraction or repulsion, I get 0. This is a channel analog to channels with non-zero angular momentum for rotational invariant case. I do screening, I do exactly what, in fact, Fein-Lauser did, let's be accurate, it's just second order. And by doing this, you immediately see interesting fact, which at this stage, let's take a zoology, and then we explain where physically it comes from. That interaction between pockets becomes more repulsive than interaction inside pockets. And you may say, well, it means that the system becomes even more repulsive. Yes, it does. But notice that this guy, G2, comes with minus sign here. And as such, it actually good for superconductivity. So you find out that eigenvalue is negative, means superconductivity develops. But then you ask a question, what kind of superconductivity develops? And not surprisingly, because this guy comes with negative sign, what comes out when you solve 2 by 2 problem, you find out that the sign of the order parameter and hole and electron pockets is opposite. Or you can, if you want, you can put it some superconductivity breaks U1 symmetry, then the face of the gap at hole pocket is opposite, differs by pi from the face of the gap in electron. This goes into nickname of sign changing S wave or S plus minus, but it's sign changing gap. Why it's called S wave? Because if I make a circle here, I'm trying, probably I need to go back to, just a second. where's pointer option? Just highlighter. Yes. So if I just go here, make a circle around this point, then gap doesn't change sign. So in standard notation of what is the symmetry of the gap, or order, by gap I mean superconducting order parameter, then you find that it doesn't change sign, it's S. So you see, story here is almost trivial. Let me, I did something wrong here. What I do in color now. Yeah, okay, let me do pen. So what you see is that you basically get, by trivial way, pairing state, which is not conventional S wave, and you get it out of screening. And then next question is very simple: experiment. What experiment tells you? Well, first of all, experiment tells you that yes, this is S wave. Why it's S wave? You look at measurement. I put several measurements here. This is one of the latest one. Gee, I'm doing something wrong about pointer options. Let me go back to laser pointer. So it's just slow with terms of laser pointer. These are measurements of the gap along the Fermi surface for all possible pockets around or Fermi surfaces around gamma point. And you see gap is constant, as I put by plus sign. It doesn't change sign, doesn't along the Fermi surface. So it's definitely S wave in this notation. That's simple. It's S wave. A little bit more difficult is how to prove that it's not simple S wave, that this gap changes sign. And if you ask theorists, they will tell you that if the gap changes sign between two Fermi surfaces that differ by some moment, in this particular case pi pi, that look at spin response, at spin susceptibility, at this given momentum as a function of frequency, and you find that it has a resonance below twice the gap value, twice the value of the superconducting order parameter. There is, if you like, effective attraction in this plus minus channel that creates this bound state in the spin channel below twice the gap value. And this is nothing but a standard, simple BCS-like game of coherence factors. So for theorists, it was really straightforward to see this. And here is experiment. This is neutron scattering done above and below superconducting TC. And you judge by yourself. This is exactly at momentum pi pi as a function of frequency. And you clearly see that above TC there is nothing. But you go below TC, you start creating a peak, pretty much where you expect it in theory. And this was considered as a very strong evidence that yes, you get sign changing S wave superconductivity. And you see, it took me a few seconds to get it. So it's really like screening immediately gave me attraction in a channel where interaction between pockets is more repulsive than interaction inside pockets. And it turns out that more repulsion here means that superconductivity wins. It's impossible not to talk about cuprates, and I will try to minimize the story again. Yeah.
Could I interrupt you?
Go ahead, go ahead.
If you have electrons and holes, would be excitonic insulator phase be stable at some special, on some range of dopings?
The answer is yes. At this stage, you will see it, and hopefully I will still have time to go into that part. You will see this competition with excitonic insulator, absolutely. At this stage, I'm just saying what happens in perturbation theory for the interaction only in particle-particle channel. I'm not asking about competitors.
Okay.
A little bit later, I will ask a question about what is a competitor to superconductivity. So yes, you are absolutely right. But notice that at this stage, although I said hole and electron pockets, I didn't use it at all.
Okay, sure.
I just said one pocket, another pocket. And I don't care whether it's hole and electron. Because superconductivity by itself, as you know, you pair two fermions on hole pocket or on electron pocket. You don't pair between them.
Yep.
Very good. Then cuprates, very quickly. Formally, phase diagram is very similar. You get magnetism at zero doping. You dope by holes or doped by electrons, you get superconductivity. And Oleg is here, and Oleg did number of wonderful works about both magnetism and superconductivity on this. And guess he was the first to realize how superconductivity can emerge even if the system has magnetic order. But I want to do something very simple here. I want to come from overdoped side, somewhere from here or from here. Experiments are mostly done here, so I come from this side. So I don't want to go into this very highly and heavily debated and hotly debated subject of pseudo gap. I want to be somewhere here and see what about superconductivity somewhere here. And then we look at experiment and we see this is a measured Fermi surface. This is quantum oscillation measurements, which show a nice Fermi surface. It's what is called open electron Fermi surface, or if you take these four pieces of the Fermi surface, you will get one circle around pi and it will be whole Fermi surface. But what we need at this stage is very simple knowledge, that the density of states where most of electrons are concentrated are at the corners. So what I want to do, I want to play a very simple game, very similar to the game I played for iron-based materials. I want to consider, instead of two Fermi surfaces, I want to consider two patches. There will be one patch at point 1, another patch at point 2, and I don't consider another two patches because I will consider spin singlet superconductivity, in which the gap at point 1 will be exactly the same as the one that my laser pointer tried to stabilize here. So this is also point 1, and this is point 2. So then I play exactly the same game as before. I said there is a repulsion for fermions within this range. Again, I selected this range simply because density of states is the largest. And there is an interaction, repulsive interaction, again, G1 for fermions in another range, and interaction G2 between them. And I play the same game with the same result. That if I start with...
Andrey, could I interrupt you?
Sure, go ahead.
I have a dumb question. If you look at this like a puzzle, you could rearrange them and to get a ring. Would it be just Fermi line close to the just to the circle?
Say it again.
If you just rearrange it, I don't know, top left, going right, you could
right. Yes, you'll get a ring
and get a circle.
No, it will not be a circle.
Oh,
it will not be a circle. Yeah, because otherwise density of states will be the same everywhere. No, it will not be a circle. There still will be ranges where this circle. Sorry, I'll be careful. There is even if it's circle. Right? Let me backtrack for a second.
It's deformed.
Even if it's circle, the question is how close the circle is to the boundary of the brilliant zone.
Mm-hmm.
This is where density of states plays a role. If the circle intercepts with the boundary of the brilliant zone, density of states goes to infinity. This is 1/2 point.
Okay.
So it will be a circle. Sorry, it's not exactly a circle, but to first approximation, we can say it's a circle. But it's a circle which comes closer to brilliant zone boundary near these points 1, 2, 1 prime, 2 prime, even if it's just one circle around pi.
Mm-hmm.
And I'm interested in the points where the Fermi surface come close to the brilliant zone boundary, because this is where density of states is resonantly enhanced. And density of states enhanced means this is where most fermions are located, density of states, where number of fermions per like unit area in K space.
Okay, thank you.
So very quickly, let's finish this part. Again, two interactions, G1, G2, we do exactly the same stuff, get the same result. Repulsion between regions, patches, I call them. Previously, there were pockets. Now they're patches of one Fermi surface. Again, favors a state where the order parameter changes sign between patch 1 and patch 2. And this comes because repulsion between these patches, when I take two fermions from one patch and put into the other, this interaction with momentum transfer to 2 pi becomes larger under screening than the interaction within patch. You will say, well, it's the same as for iron-based with the only change of the word from patch to pocket. Yes, it is, with one exception, that because plus and minus are parts of the same Fermi surface, in between I must have zero. And once I extend this everywhere, I found that there should be 4 zeros. 4 zeros means that this is D-wave superconductor. And without going into long discussion about D-wave, etc., here is one of the experiments for which Buckley Prize was given. It's a measurement of modulus of the gap, mod delta, modulus of the ordered parameter, let's call it accurately, as a function of the angle. And you see that it goes to zero practically exactly at 45 degrees, where it's supposed to go. So this was really considered as very, very strong evidence that this is D-wave. So you see, what I'm trying to say here is that cuprate is a big story. Oleg knows that better than me. There are a number of theories for how antiferromagneticism dies, how pseudogap develops, what is pseudogap, etc. But if you ask about pairing symmetry, it comes immediately as D-wave from this kind of consideration. An experiment, I guess nobody right now doubts that it's D-wave. The last example I want to give you will be, again, pretty much the same, but consequences will be a little bit more interesting. Let's consider superconductivity in a single layer graphene, and possibly the same works, at least there are a number of papers who said that the same mechanism works for twisted bilayer graphene. What I want to do is this. I want to consider a single layer graphene, the one that mostly known by Dirac physics around K and K prime points. But this is at charge neutrality. Let me take this graphene and dope it, putting chemical potential up, away from Dirac point. I start opening Fermi surfaces. It's just, if my laser pointer will show, it's basically like crossing at finite energy. It's probably better here. You start creating first circles and then triangles like near K and K prime points. And then at some point, these guys merge. And this merge at points M1, M2, M3. And then you opened up a large Fermi surface, which is centered at gamma point. And this is most situation, again, most favorable for any instability, because this is the point M when Fermi surface crosses brilliant zone boundary, where density of state formally diverges. It's called Van Hoff point. And let me play the same game. Suppose that I'm at this doping. You may say whether it's experimentally reachable. The answer is yes. There are photo emission experiments from Berkeley, from Caltech, that shows that yes, you can reach this by doing some pretty sophisticated experimental stuff. Then I get 3 points now, 1, 2, 3. They're all equivalent, at which Fermi surface crosses brilliant zone boundary. This is where density of states is the largest. Total number of these points is 6, but again, for spin singlet superconductivity, what happens is 1 at point 1 is the same as what happens here. What happens at 2 is the same as what happens here. And this is just like 3. So I have 3 points, but what's the number of interactions? 2. Again, either repulsion within pocket, within patch, sorry, or repulsion between patches. And because 1, 2, 3 are equivalent, I can only write down 2 interactions. You may say, well, big deal. Solve 3 by 3. It's again trivially solvable. You get 3 eigenvalues. And then you find that this one is uninteresting. It's completely repulsive. And not open a secret, this conventional S wave. But then I have 2 others, not 1, 2, that are again difference between G1 and G2. The rest is same story as before, same result. You screen, and by screening, you find that in interaction G2, repulsion between patches, again becomes larger than the interaction within a patch. You win. Lambda becomes negative. Great. But there are 2 of them, and they're degenerate by symmetry. As a result, you get two D-wave-like states. I call it delta A and delta B, and I plotted it how they behave in the 6 points that I labeled. We discussed 3, but again, other 3 are just the same by symmetry. And they're both D-wave, meaning that they change, the gap changes sign 4 times when I make a circle. I can call them whatever I want to call them. But it's important there are 2 of them, and they're degenerate. And then you ask the question, do they appear together? And the answer is yes, they appear together. But moreover, they appear with relative factor I. Means the phase of one is pi half differs by the phase of the other by pi over 2 or minus pi over 2. And therefore, with this simple analysis, you immediately find that the state which you get will break time reversal symmetry. This will be chiral superconductor, and in each of the states, phase will wind up by either 4 pi or minus 4 pi when I make a circle around the Fermi surface. And because it's a combination of term even under inversion and term odd under inversion, this really chiral superconductor, changing sign I to minus I is the same as doing inversion. So again, simple analysis, nothing special, and you get chiral superconductivity. And because it's chiral superconductivity, as I said, when twisted by superconductivity and twisted bilayer graphene came in, I think the number of papers that said it should be D plus ID was definitely more than 10. Great. Now I need to know how much time I have. Do I have to stop here, or I have some time to go at least through the...
We are happy to continue.
Okay, you stop me when you say enough is enough, okay? Now, with all this, next statement is, guys, it's too good to be true. It's too simple. Although the outcomes is D-wave for cuprates, S plus minus for iron-based, both confirm experimentally, this D plus ID or D minus ID chiral superconductivity for graphene, which was in single bilayer graphene, people searched, but so far didn't find it. I didn't find any superconductivity for in this case. It's just a question about temperatures, etc. Why it's too good to be true? Because, and I made the point 20 minutes ago, assumption was that the Bayer interaction is Hubbard. It's not Kohn-Luttinger in a rigorous sense of the word. It's really Fey-Lauser stuff. And then you start with 0 in the channels that you are interested in. And then very small disbalance between 2 couplings. One was inside patch or pocket, and another was between patch or pocket, was enough to create attraction. But you may ask, well, what is reality? Reality is not Hubbardian. Reality is that you consider the first order in coupling, which is, I wrote this many times before, G1 minus G2. And let's rephrase it like this. G1 interaction at small momentum transfer. G2 is interaction at large momentum transfer. You go from one patch of pocket to the other patch of pocket. Great. And you ask any person, you take screen Coulomb interaction. Originally, 1/r. Yes, it's screened. But what is large? By any means, interaction at small momentum transfer will be larger than interaction at large momentum transfer. So in reality, if you go away from Hubbard interaction and back into screen Coulomb interaction, you say, I should start with repulsion. And what I presented to you so far was just pure perturbation theory, which is great when you start perturbation theory with nothing at 0 order, at first order. Now I'm telling you, start with repulsion at first order. And within perturbation theory, there is no way how you can start with repulsion and convert it to attraction, because this is nature of perturbation theory. Second order term is smaller than the first one. So then somehow the Kohn-Luttinger effect in spirit screening has to overcome initial repulsion, and you cannot get it in perturbation theory. For those who may remember what it was, I would say physicists, we have a problem. Although when I read about this, interestingly, just 10 seconds about this, it turns out that the phrase that everyone knows, Houston, we have a problem, is correct but not precise citation of what was actually said. The two phrases that were said are similar but not the same as the one that was done in the movie about Apollo 13. So, but nevertheless, that's a problem. How can one go beyond second-order non-perturbation theory and enhance Kohn-Luttinger effect? I want to do it in a controllable way. Otherwise, you know, I can wave the hands and do something, whatever. And the answer is yes, we can do it, interestingly enough. And this will bring me also to competition with some other orders. Namely, that what I will tell you in the next few slides, it goes under the name Parquet renormalization-group analysis. And it goes like this. Again, let's go back to pnictides. That's why I started with the pnictides. You probably heard this too many times. Two interactions, and you need G2 larger than G1, and you start with G1 larger than G2. So how can I control my calculations and change the sign of the interaction? And basically, this is what I already said. We know example. We know in examples when we can start with perturbation theory and do perturbative calculations to infinite order, and we know that we must do this. It's called superconductivity itself. I'm not opening any secret. We started with Cooper logarithms, and we know what have to do with superconductivity. Interaction can be weak, generally G, but in order to see superconducting instability, again, we need to include G. Next term will be second order G squared, but I multiply by log. Next term G cube, I multiply by log square, etc., etc. And this is how I get bound state, essentially. This is another way to say that because of this Cooper log, I will eventually, higher order terms will be larger and larger. But in doing this, I include G square log, but I neglect G log because G is small. I include G cube log square, but I neglect I include G cube log square, but I neglect G cube log and G cube, of course. So if I have logarithms, I know what to do. I can combine coupling with log and then sum up series. And for superconductivity, that's the way to go. But I told you that Kohn-Luttinger normalization is screening. For screening, you normally don't expect any logarithms to appear, except that at this stage, we'll start playing the game that one Fermi surface of electrons and one Fermi surface is holes. And the story is really story about excitonic insulator. It's part of the story here. Namely, I want to say that if you want to screen and ask what you get out of screening, screening comes, it's again, what you do. You take interaction in the particle-particle channel and want to calculate irreducible interaction. You screen it in a particle hole channel. But because one fermion can be at hole pocket and another at electron pocket, when you calculate particle hole bubble, you find that it's undistinguishable from particle-particle bubble. It gives you the same log 1 over T. The trick here is that for particle-particle bubble, we have equal energies and different frequencies, omega and minus omega. Here we have the same frequency, but different sign of energies. So up to sign, overall sign, it's the same. And you get logarithms in a particle hole channel. This is the logarithms that give you excitonic insulator. In fact, I will rephrase it in slightly different wording, but it's the same as excitonic insulator. And then you can say, wow, good. Let's try now to play the game with logarithms. But for this, I must say that you cannot separate particle-particle and particle hole channel. Both give you logarithmical singularities. So instead of saying that let me screen interaction and then use screened interaction and do standard BCS-like calculations, what I want to do is to say, look, I want to consider on equal footing screening and any renormalization in the particle-particle channel, any standard Cooper logarithm story. For this, I need to introduce, first of all, of course, the same as we had before, two types of interactions which are responsible for pairing. Dashed line is, say, hole pocket, solid line, electron pocket. And again, remember, G1 is repulsion within pocket. G2 is pair hopping. When I take two pairs of fermions from one pocket and translate into other pocket. These are two interactions relevant for superconductivity. But I also take two interactions in a particle Hall channel. And this is density and exchange interaction. And this is the ones that are responsible for Kohn-Luttinger normalization. And Kohn-Luttinger normalization will be as logarithmical as the one in particle-particle channel. And there is a wonderful mathematical apparatus how to do calculations in this situation. And it goes under the name Parquet RG. Instead of cranking series of logarithms order by order, etc., you write differential equation and solve them. Differential equation for what is called running couplings. They are all functions of logarithm of a running energy at which I plot the system. W is just upper cutoff for the energy bandwidth. And these equations are exact in the sense that they are obtained, I can obtain them diagrammatically, order by order, by summing up leading logarithms. So this is what comes out when I sum up leading logarithms. And then you find out that two interactions, G1 and G2, here are the guys, G1 and G2, are somehow coupled to the interactions in the particle Hall channel. And that interaction, G3 and G4, they live their own life. They also undergo logarithmical normalization. And then I can solve these equations. Mathematica, by the way, can solve them in a second, but I can even analytically try to do something. So here's what we need to understand. We start our story with two interactions in a particle-particle channel, one good guy, one bad guy. G2 is good guy, G1 is bad guy, and bad guy is larger than the good guy. I solve these equations. Here is what I get. It's really, to me, it's really a fantastic thing. When the system self-generates a scale below which it converts repulsion into attraction. You see, good guy goes up, bad guy goes down, and this is all a solution of these equations. And then you find that there is a scale inside where initial repulsion total becomes attraction. And what's important, my couplings are still small. This all works when G times log is of order of 1, but G is by itself is still small. So this is a completely controllable calculation in which I convert repulsion into attraction in the regular ways. So this tells me that in iron-based superconductors, even if I start with repulsive interaction initially, there is a way how I can convert it into attraction. And at this stage, of course, the question is, where's the physics? What's going on? So physics is this. It's what Dmitry asked. There is another interaction. So first of all, what equation tells you? Equation tells you that there is a guy, which I call G3, interaction in a particle Hall channel. This by itself is this interaction is not responsible for, is not participating in superconductivity. But what it does, it goes up under this Parquet RG, meaning that it increases. As it increases, it pushes up good component of the pairing interaction G2. That's what it does. So it goes up by itself, and by going itself, it takes with it also interaction G2 and pushes it up. And when the interaction of G2 grows, it in turn pushes down that component of the interaction G1. So this explanation why one goes up, another goes down. But this is explanation. Here are the equations and how I solve the equation. When you ask a different question, taken alone, what this interaction G2 will give you? It's a repulsive interaction, and it just grows. And suppose I looked into this channel, and you found that this guy, the pusher, by itself, give rise to a special spin density wave instability, which is another name for excitonic insulator. So this is magnetic stripe magnetic order that comes out from this interaction G3. And at this moment, something smells. We have what we have. We have a system which initially have repulsive interaction in the particle-particle channel, but there is one interaction that pushes system, goes up and pushes system closer and closer to magnetic instability. And when the system becomes closer and closer to a magnetic instability, this growing interaction in a spin channel effectively creates attraction in a plus-minus pairing channel, which means that this is a really intelligent way to say that attraction is induced by spin fluctuations. And this is essentially how you get spin fluctuation mediated superconductivity. This is just a rigorous way to do this. A little bit less rigorous way is just to abandon parquet RG and just use a series of ladder graphs for renormalization of the pairing interaction. But either way or another, what happens is the system tends to become magnetic, and magnetic interaction, when it tries to develop, it increases good component of the pairing interaction and produces your attraction in, say, here in S plus minus channel. If I do the same for cuprates, I find that D-wave attraction is magnetically mediated. Magnetic interaction also give attractions as D plus ID and D minus ID channels. So what I'm trying to say here is that if you look carefully, what this Kohn-Luttinger in spirit effects tells you, it tells you that in fact, the reason why you get this good interaction going up is because it's pushed up by magnetic fluctuations. The reason is that this interaction has the same momentum as momentum for magnetic instability, and two interactions with the same momentum are actually supporting each other.
Andrey, could I interrupt you?
Yes, please, please.
You have presented the dependence of G1 and G2 on the energy scale. What happens with how would look for G3 and G4 if you plot them together? What's the
G3 goes up, G3 keeps going up, G3 keeps going up, and G4 goes down, changes sign, and then becomes negative. This is what happens. But G4 is not that relevant for us. G3 goes up. The question you are asking is this. Again, I put this under the rug a little bit. What I said is when G3 is going up, then interaction in the pairing channel becomes attractive. But I did not say who wins, what the system does first. And this is a separate story, which I already, well out of time, I decided not to talk about. Short answer is this, that if you start with truly very weak coupling, the very fact that in a particle-particle channel, in this situation, you get what is called log square, because one log comes from the renormalization, another comes from this particle Cooper channel itself, while G3 contains only a single log. Eventually, interaction in the particle-particle channel will win, and the system will develop superconductivity. But this is at extremely small coupling when I can run RG for long energies. If I say I start with effective attraction in S plus minus, in spin density wave channel, because to develop magnetism, stoner magnetism, come from repulsive interaction. So I don't need to change any sign here. And then I will need to wait before pairing interaction becomes attractive. Then you can say, well, I have a finite temperature of instability, which means that I end my RG flow at some finite scale. Then everything depends on initial condition. And in particular, I may have a situation when the system first develops magnetic instability before superconductivity. What happens is a pretty standard game in real life rather than physics, is that when two instabilities tend to develop, they support each other. As I said, magnetic instability, which is about to develop, increases attraction in the S plus minus channel. You can equally say that attraction in S plus minus channel keeps pushing up interaction in spin density wave channel. But when one order develops, it will do everything it can to kill other order. So competitors are not allowed. When order develops, it starts immediately killing all competitors, which means that when order develops, it develops forever. except for tiny range when it's close to the boundary and two orders can happen. So short answer to your question, I gave long answer, is that depending on initial condition, for this RG equations, the system can develop either magnetism, the stripe magnetism, or superconductivity, and some more exotic state when both order develops are also possible when two interactions are very close to each other.
Okay, thank you.
My goal here was just to say that when system tends to develop magnetism, it creates attractive interaction in a pairing channel. This is how one can replace, one can go from repulsion to attraction in a sort of controllable way. Okay, so let me very quickly just at least outline the last thing I want to say. At one say, we can stop here because great, we got attraction. And even if we started with repulsive interaction, we know how to get attraction. Well, let the system tend to develop magnetic order. Then we're pretty much guaranteed that at some point, system will convert repulsion into attraction. People did number of calculations of this kind, not necessarily, as I said, parquet RG. In some cases, instead of parquet RG, people just did sort of RPA-like calculations and found that exactly the same happens near a nematic transition, near a charge density wave transition, near a transition into current state like circulating current. In all cases, there are conversion of initial repulsion into attraction, and you get attractive pairing interaction. And you may say, well, are we done? Well, we may say, well, we are done. But there's one exception here, that we now go into different and previously unexplored range, because we said there is interaction which tends to order system in a non-superconducting fashion. And in the process of doing this, it also creates as a byproduct attraction in a pairing chain. But there is one extra element of this game, namely same interaction, magnetically mediated interaction, in the case that I consider, that give rise to attraction, also does something else that I didn't consider before. It destroys coherent fermionic behavior, which goes under the name destruction of a Fermi liquid. And it makes fermions incoherent. And then remember the story I started with, Cooper logarithms. Cooper logarithms were great when the Fermi surface excitations are sharp. If excitations are incoherent, there is no such thing as Cooper logarithm. And therefore, we enter in the new field where on one hand, we don't need to answer the question I posed as a question for the talk. How to get attraction from repulsion? We got attraction from repulsion. We now need to ask a different question. Do we now are we guaranteed that if we have attraction, we get superconductivity? Previously we were, because we said Cooper effect works all the time. Arbitrary weak attraction is always sufficient for superconductivity. It may be some other order develops first, but if we forget about some other order, superconductivity is guaranteed to develop. Here, the answer is not guaranteed. We have incoherent fermions from the same interaction. And I have about 10 more slides, so I will not really go into all this. I just want to say that there is a real competition. Tendency towards non-Fermi liquid is opposite to the tendency of superconductivity by one simple reason. Strong fermionic self-energy, the one that creates fermions as incoherent, acts against superconductivity simply because it destroys Cooper logarithms. Cooper logarithm works well when fermions are free particles. When fermions are incoherent, you don't have the story that you have effectively two-dimensional, 1 + 1 dimensional, and you get always bound state. Simple reason that self-energy goes as omega to power smaller than 1, and so as a result, you don't have this 2 powers of frequency and energy, quasi-particle energy in denominator. You get something smaller. Dmitry, I need to ask a question here. I can stop here, or I can go and explain the stuff that I'm really working in. What happens instead of BCS? What happens when we have incoherent fermions? You tell me what to do.
As you prefer, we're happy to continue.
Really?
Yeah.
Okay, then few more minutes, really few more minutes.
Sure.
There is new element which I already said, but not explicitly here. And the story is that what is incoherence? Incoherence is the consequence of the fact that interaction becomes dynamic. Yes, you do screening, but remember that any screening is dynamical screening. Inside of the screening, there's Landau dumping of any boson into fermions. So any screening by fermions involves polarization bubble. Previously, I talked about this bubble as a purely static, but in fact, it's dynamic. And therefore, interaction mediated by any, what I call soft boson, meaning any fluctuations that of order parameters that about to order, like magnetism, is by definition dynamic. It's retarded interaction. And you may say, well, what's the big deal? We know it's in books. Electron-phone interaction is retarded. Yes, but here we have a new part of the story. That if we are close to a point where the system is about to develop another order, and we want to study whether superconductivity developed before the system develops this other order, then we have interaction mediated by a truly soft boson. It's just like you take Debye frequency, effective Debye frequency, and make it smaller and smaller. Then retardation becomes the major effect. And what happens is that, like you take electron-phone interaction and make Debye frequency smaller and smaller, interaction by optical boson, you find the interaction that is effective interaction is 1/omega squared. Here, generally, there is a set of models in which effective interaction mediated by soft boson, after I do all the standard machinery of selecting pairing channel and dual momentum integration, it becomes singular function of frequency. It goes as frequency goes to zero, not to a constant, which would be the case in conventional BCS, but it goes as 1/omega to with some exponent gamma, and quite a large number of people and quite a large number of different gammas have been considered. If I consider system near a spin density wave transition in 2 dimensions, exponent is 1/2. If I consider system near a pneumatic transition as 2 dimension, exponent is 1/3. There is wonderful development related to actually SYK coupled SYK fermions, means dispersionless fermions in the quantum dot coupled with Einstein phonons with a random Yukawa coupling. And it turns out that this model reduces to exactly the same one I showed with varying exponent, which depending on the ratio of number of fermions and number of bosons can be any number nowadays between 0 and 2. There are 2 versions of the model. What I want to do, I want to, first of all, show you simple equations that we need to solve. This equation for self-energy, this equation for what is called anomalous self-energy, pairing vertex. This knows about superconductivity. This knows about non-Fermi liquid. Computation is trivial. Look at denominator. The larger is self-energy, the smaller is, of course, the smaller is kernel equation for phi. Opposite is also true. The larger is phi, the smaller is kernel for self-energy, which means that if you have superconductivity, you gap low energy excitations and the system becomes Fermi liquid. But we now want to look into whether we can get a solution with non-zero phi. And notice that for this, I need to consider what's called linearized equation for phi. When I take phi as very small, I see whether it can develop. And I look then at sigma self-energy in the normal state. Sigma tilde, I just incorporated bare omega into self-energy. And if we start with BCS case, which is gamma equal to 0, then self-energy is linear in omega. So this is omega. Then you can check immediately, you get BCS. You can call it a Liashberg theory, but it's essentially not qualitatively not different from BCS. Then you get Cooper logarithms, you're guaranteed that you get superconductivity. If I take any non-zero exponent, which means that I'm close to a point where the system is about to develop non-superconducting order, it turns out that I start with a state which is non-Fermi liquid, which has self-energy which goes as omega to exponent 1 minus gamma. And this is really non-Fermi liquid because it means that both real and imaginary part of this self-energy, this is all Matsubara frequencies. But you convert to real frequency, you found both real and imaginary part are of the same order and both larger than bare omega. By definition, this is non-Fermi liquid. The point I want to make, and I probably don't need more than 2-3 minutes for this, that pairing mechanism in this situation is qualitatively different from BCS. Let's start for this from BCS. So what I will do something which explores Cooper logarithms. I will look at the linearized equation for the pairing vertex, or I add some bare phi naught, some infinitesimally small pairing into the problem, and then calculate response to this phi naught. Basically, I calculate phi, putting in phi naught. Dividing phi by phi naught, I get pairing susceptibility. We know that superconductivity develops when pairing susceptibility diverges. And when pairing susceptibility changes sign, this is guaranteed that something happened with the system, that you have superconducting instability. We know how to do it. Let's start with BCS. This is, in my case, gamma equal to 0, constant interaction. You write gap equation like this, linearized equation. You don't need to sum logarithm to solve this equation, but let's sum logarithms. Let's do it iteratively. I start with phi naught and then calculate phi order by order. I'm doing BCS. Here's what you get. You get phi as phi naught, the next term lambda log, next term lambda square log square, and I assume again that lambda is small, I sum up logarithms, and you get standard BCS result. That susceptibility phi divided by phi naught is 1 divided by 1 minus lambda log, which means that this susceptibility diverges at a finite temperature, which is upper cutoff E2 minus 1 over lambda, standard BCS result. Meaning any small lambda will give you instability because lambda gets multiplied by log T. Wonderful. This is BCS. Summing up Cooper logarithms. We return back to the very beginning of the talk. Now let's take finite gamma and do exactly the same, but now we depart from non-Fermi liquid state. Here's how linearized gap equation looks like. A little bit different, but now we see what the ingredient is. This omega to power of 1 minus gamma is self-energy, which at small frequencies is larger than bare omega. This is why I keep it here. This difference between internal and external frequencies to power of gamma is my interaction, which is not a constant, it's singular functional frequency. Both small omega and large omega are fermionic frequencies. Their difference is bosonic. So you get one component from self-energy, one component from the interaction, and then you ask, wow, what is the total power in denominator? Sometimes, what is the scaling dimension of the kernel? And you find that's 1 minus gamma plus gamma, 1. So it's like in BCS. I get 1 over omega by order of magnitude estimate. So immediately then I get logarithms in when I do iterations. So I start with phi naught. Next term will be phi naught squared times log. Let's do it. Here is the result. Phi is equal to phi naught. Next term is log. Next term is log square. But minor thing, there is 1/2 coefficient here. Next term will contain coefficient 1/6, etc. And you see what happens. Sum of the log, this is exponent of the log, power. So I get it here. And you can say, well, now I divide phi by phi naught. I do it even at 0 temperature. And I get something positive, which means that susceptibility is positive. Non-Fermi liquid prevented for development of superconducting instability. Summing up logarithms, I get nothing. And this is the key difference with BCS here. And you may say, well, what are you telling us? You are telling us that there is no superconductivity. Then why we spend 1.5 hours before talking about attraction, etc. And here we notice that, yeah, we did something. But previously, we get coupling lambda, and I said many times, lambda is small. This is how you can solve logarithms. Now you see coupling, and you see there's no smallness here. It's a number. 1 minus gamma stands here, number. You may say, what happens with gamma close to 1? I didn't put what is under the logarithm. If gamma close goes to 1, there is a singular term here, so it's not small anyway. It's generally coupling of order of 1. So I cannot sum up logarithms here because I neglected higher order terms. I neglected term 1 minus gamma squared times log here. I summed up the only leading logs. So let's not do it. Let's go back. Let's ask this guy with a magnifying glass. And the guy with magnifying glass tells you, don't sum logs. You don't need to. You get a kernel, which is, again, remember this interaction, this self-energy, and total power is 1. And we don't need to sum logs because we know that in this case, solution must be a power law. Absolutely. This power law with some power, because if I put power in, I get the same power out, and all then I have to do is to connect or equalize left and right hand side of the equation and obtain power, and phi naught will be just overall factor. Good, I can do this trivially. By the way, what I had before, very quickly, remember, I got power. So I did this, I got power, but it was real power. Now I do actual calculations. This is just straightforward calculation. I put power, some power alpha, put in this equation, and solve for alpha. And surprise, surprise, I found that no, if I do it exactly, not summing up logarithms, I get some strange thing. I get 2 complex exponents. And this fantastic thing, equation has completely real coefficients. Solution is complex exponent. What complex exponent means? It means that this phi, which I get, start oscillating at small frequencies. Because sum of 2 complex exponent, you can check this, it's trivial math. You get 2 complex exponent, and this is basically this like e to I beta log omega, and so you get cosine of beta log omega plus some phase. Long and non-complete list of people who did it. Some of the names are in high energy, some of the names are in condensed matter, because what in high energy is called holographic superconductivity is exactly what I described to you. So we come to the conclusion. So our solution oscillates at small frequencies. And now we can say, wow, at large frequencies, let's go back. If I do iterations at large frequencies, start with phi naught, put it here, everything is positive. So next term will be larger than I start with. Do iterations once again. Next term will be even larger. So this means that, that when I do iterations, I can only increase phi. And I found that at small frequency function oscillates. I cannot match them. This is inconsistent. And this inconsistency means superconducting instability. That in order to kill this inconsistency, I will need, and I will tell you what the result of calculations is. I will need to introduce a finite function phi of omega, which essentially will kill oscillations at small frequencies. Then I will be able to match with high frequency solution. And this goes under the name fundamentally non-BCS pairing mechanism, when instead of Cooper logarithms, whose summation give you nothing, you get what is called complex exponent. You search for solution in the power law, and you find that solution, despite that all coefficients are real, you find 2 complex conjugated solutions, which means that behavior at large frequencies and small frequencies in terms of susceptibility are inconsistent, meaning that somewhere in between susceptibility will diverge. Because without divergence, you cannot connect what I see at large frequencies and what you see at small frequencies. This function goes through zeros. This function only increases when you go to smaller and smaller frequencies. In between, this increase should give you infinity. And this infinity means that pairing susceptibility is singular, which means that you have non-zero order parameter. So this is a wonderful story. I like it really very much, of really fundamentally non-BCS pairing. And it was really done from two ends, from condensed matter end and from high energy end. And I will finish this talk by saying that what I told you is the tip of the iceberg. If you take phase diagram of the model that I told you, I'm only talking about how you get this onset temperature for the pairing. This line, which I label here as TP, this is where complex exponent start playing a role. You get solution, you get superconductivity. But then there are two different, topologically different phases, topological transition here, dynamical vortices, pseudo-gap physics. I'll be happy to talk about this, but you're tired. Conclusions. Conclusions are, and thanks very much for listening, really thanks. There are numerous examples when superconductivity, which requires pairing of fermions into bound states, come actually from repulsive electron-electron interaction. And the generic idea comes back to Kohn-Luttinger, because their key message, if we go away from their explicit calculations, their key message is that don't take bare interaction, include screening. Screening will give you something that in their case just give you Friedel oscillations, and they play the game with this, but general idea includes screening and see whether screen interaction may have some attractive pairing component. This gives you S-wave superconductivity S plus minus in iron-based, plus minus, D-wave in cuprates, D plus ID in doped graphene. And we know where, if we don't do it in starting from Hubbard U, then we basically know that the reason why we do get it is because the system tends to develop some other order. In the examples I gave you, spin density wave order, but you may think about other orders. And by doing this, it promotes good component of the pairing interaction. But at the same time, by doing this and solving the problem how to get attraction out of repulsion, the same interaction also makes fermions incoherent. And then there is a wonderful new story about competition between tendency towards non-Fermi liquid and tendency towards pairing. Attraction is there, but there is a competitor. And this is what gives you fundamentally non-BCS pairing mechanism with multiple consequences of this mechanism. Finally, thank you very much.
Let's thank you, Andrey, for fantastic introduction and new very inspiring developments. Do we have any further questions? Please just go ahead and just ask. I think we have a question from Yahim.
Yes, hello, I have a question. And I'm wondering, how does this all play in, does this have anything to do with odd frequency superconductivity, what you talked about? Or generally, do you have an opinion on odd frequency superconductivity? So would it appear, can it appear from purely repulsive interactions?
Wonderful, great question. Yes, I do. And I'll give you a quick answer in two ways. When you have interaction, which is frequency dependent, you can search for two types of solutions. One type is even frequency, another is odd frequency. Both are allowed. You can write two different gap equations and check susceptibility for two different solutions. One will be even frequency, and this one about which I talked. And the other one will be about odd frequency. It will be similar, but not identical. But the story will be the same. In order to get odd frequency superconductivity, you will get exactly the same game. You will need to find these complex exponents at the critical point, and then you will get odd frequency superconductivity. But generally, once you have interaction, which depends on frequency, not even singular, but generally depends on frequency, you can search for two types of solutions. Now, in general, it happens just not matter of numbers, that in all examples I know, TC for even frequency superconductivity is larger than TC for odd frequency superconductivity. This happens. So in this respect, even frequency always wins. However, there is a way to kill even frequency superconductivity. For example, apply magnetic field. you will kill even frequency superconductivity. Odd frequency superconductivity will be not sensitive to this addition, and therefore there is a possibility to have a range where odd frequency superconductivity wins. There is one obstacle here, only one obstacle, that if you seriously take this competition between non-Fermi liquid and pairing, then, as I said, you need complex exponent. If the exponent is real, you don't get superconductivity. For even frequency pairing, you are guaranteed to get complex exponent, and believe me, it's really a proof that you guaranteed. For odd frequency, you are not. And strictly speaking, if you don't include any extra normalizations, you don't get complex exponent. But I think that with reasonable normalizations, you do get. So with this caveat, I would say that A, odd frequency superconductivity is always a possibility, always needs to be checked. Moreover, if you find a way to get it, then normally it would be secondary compared to even frequency. But if you find something to kill even frequency superconductivity without affecting odd frequency one, then, for example, just add Hubbard U to all stories. And then you will get possibility for odd frequency. That's it.
All right, thank you very much.
Okay, thank you. Do we have any other questions?
May I ask a short question since this frequency dependence, and this is very, very simple question. Andrey, can you please comment if it's unrelated to non-Fermi liquid, simple plasmon mediated superconductivity? What is the status in very, very short way?
Well, I think it's there. It can be, it can happen. Yes, it can happen. And maybe I will give you a little bit more extended answer because I expected a question like this. So this is one example of something different. Even if we get, go back to conventional electron phonon mechanism. Remember at the beginning of the talk, I said that this story is still far from being completely solved. Then you can ask a question, how small electron phonon attraction win over much larger electron-electron repulsion? And conventional answer that you can find in textbooks nowadays is that, yeah, you will see like why I'm talking about this, because I will come to your question in a second. The standard answer that you get in textbooks is that, yeah, electron-electron repulsion is larger, but if there is a large frequency window between bandwidths and Debye frequency, then in this window, electron-electron interaction goes down in the pairing channel because it's repulsive. And at some point, it can become smaller than electron-phonon interaction. This is what you can read in some modern textbooks, not all. In some that are going beyond this, the answer is more precise, that no, this is technically not quite right statement. You never get attractive interaction as a combination of electron-electron and electron-phonon one. Because if you want to screen electron-electron interaction, electron-phonon interaction is part of screening of electron-electron interaction. And short answer is this. You get total electron-electron plus electron-phonon interaction, which remains repulsive. You still get the story with repulsion. But then this interaction, due to electron-phonon part, this interaction is reduced at smaller frequencies and compared to large frequencies. And then you search for the solution for the gap, which changes sign as a function of frequency, and try to adjust sign change to get a solution. And the answer is you get this solution. So the solution of conventional problem for electron-electron plus electron-phonon interaction is the gap function that changes sign between large and small frequencies. Okay. The story which we see in some of the textbooks is the story like this. Let's integrate out high frequencies and obtain effective theory for only low frequency gap. This is what goes into Macmillan lambda minus mu star, etc. Going back to Alex's question, pairing due to plasmons
No
belongs
phonons.
to this. Sorry.
No phonons.
No phonons, no phonons. Nevertheless, screening produces you frequency-dependent interaction. And then because of frequency-dependent interaction, you try to search for the gap function that changes sign as a function of frequency. And the answer was that you find this solution. So you play like for the story that I told you, that was the sign change in momentum, like D wave for S plus minus. Every time you've tried to basically say interaction is repulsive, but you can essentially incorporate this repulsion into sign change of the gap function. Here you do the same. Interaction is repulsive, but it's frequency dependent, and you try to incorporate this repulsion into sign change of the gap function. And this is what I know. And claim is that you do get solutions, starting from Tanaka and more recently Ruchman and Patrick Lee. They all found that yes, you will get solutions.
Thank you.
Thank you. Any other questions? Just please go ahead and ask. If not, let's say Andrey again.
Thank you very much for listening, and sorry for going that much over time, but well, thanks.
Yeah, nice to see you
Thank you.
again. We'll see you in a month.